Today we will be solving this problem called exponentiation 2. It is a continuation of the previous problem, exponentiation. So I invite you to solve that problem before moving on to this one. So here our task is to efficiently calculate values a raised to the b raised to the c modulo a billion and 7. And we will have to answer n queries, n being up to 10 to the 5th. And for each query we'll be given 3 integers a, b, c, and these integers can be as large as a billion. So let's go to the drawing board and see how we could solve this problem. So we saw from the previous problem how to compute a raised to the bth power very efficiently using binary exponentiation. And we said that we would be able to do that in O of log of b. And today we will see how we can expand this approach to solve the problem at hand, and that is to answer a raised to the b raised to the c. So our challenge in this problem is transform this form into one that we can solve, and that is x raised to some y power. And the first idea that might come to mind is that since we want to calculate a raised to the b raised to the c modulo our mod that is a billion and 7, we could think that we could start by computing this modulo mod also, and then just substitute whatever we get here and raise a to this power using this previous technique. But will this actually work? So let's say, for example, we want to calculate 2 raised to a billion and 7 raised to the power 1. So if we start by calculating this, so a billion and 7 raised to the first power is equal to a billion and 7, and this is equal to 0 mod a billion and 7. So this will actually give us 2 raised to the 0th power, which would be equal to 1. But 2 raised to a billion and 7 is actually not equal to 1. It is actually equal to 2. And we can use the program from our previous problem to check this. So here, if I check 2 raised to the 2nd power, for example, it would give me 4. And then 2 raised to a billion and 7, this will give me 2. And as I said, a billion and 7 raised to the first power will give me 0. So if I just went ahead and calculated this will give me 0, and 2 raised to the 0 is equal to 1 and is not equal to 2, which is the correct answer. Therefore, we cannot just take this, calculate our modulo, and then substitute. However, this approach is not too far from the correct approach. We indeed need to simplify this power here, and we will do this using a famous theorem in mathematics, and that theorem is Fermat's Little Theorem. So let's check it out. So as you can see here, Fermat's Little Theorem states that if p is a prime number, then for any integer a, the number a to the p minus a is an integer multiple of p. In other words, a raised to the pth power is congruent to a mod p. And in addition, and this is what's relevant for us, if a is not divisible by p, then Fermat's Little Theorem is equivalent to the statement that a raised to the pth minus 1 is congruent to 1 mod p. So we have an example here. If a is equal to 2 and p is equal to 7, then 2 raised to the 6th power is 64, and 64 is indeed congruent to 1 mod 7 because it's equal to 63 plus 1. So I went ahead and rewrote the theorem we just saw. So if p is a prime number and a billion and 7 is indeed a prime number, and p does not divide a, and as our integer a is a and b and c are less than or equal to a billion, and our prime is a billion and 7, then p does not divide a. Therefore, we have that a raised to the p minus 1 is congruent to 1 mod p. So let's go ahead and prove this theorem really quickly, then we will go back to see how it will help us solve our problem. So let me consider all the multiples of a up to p minus 1 times a. So I'll have a, 2a, 3a, 4a, and so on up to p minus 1 times a. Okay, so I claim that any of these number modulo p is different from any other number. So more formally, suppose I have two values here, two multiples of a, say r times a and s times a. And I claim that r times a is different from s times a modulo p for all r and s. And I will prove this by contradiction. So suppose r times a is congruent to s times a mod p. So I can bring everything to one side and factor out an a. So I'll get a factor r minus a is congruent to 0 mod p. So this product is divisible by p since it is congruent to 0 mod p, and since p does not divide a, it must divide r minus s. So therefore r minus s is congruent to 0 mod p, and this implies that r is equal to or is congruent to s mod p. And since r and s are strictly less than p and they are congruent to each other mod p, therefore r is equal to s. And since here I started claiming that r and s were different, I got to a contradiction here. Therefore my claim was correct, and that is for all r and s such that r is different from s. R times a is different from s times a modulo p. Therefore, all the multiples of a from 1 to p minus 1 have a different modulo with respect to p. So all these values have a corresponding value from 1 to p minus 1 included, and this value is distinct for all these numbers. No two numbers share the same value. So for example, this one can have 2, this one p minus 1, this one 5, and so on. So now let's go ahead and multiply all the multiples of a together. So I'll have a times 2a times 3a times 4a and so on up to p minus 1 times a. And this will be congruent, as we said, to 2 times 5 times p minus 1, for example. These values I just made up, but the most important thing is that we will have all the values from 1 to p minus 1 included in some random order. And since we are just multiplying them, then we can rearrange them in the normal order. So this will be congruent to 1 times 2 times 3 times p minus 1, everything mod p. So on the left hand side I will have p minus 1 copies of a. So after multiplications I will get a raised to the p minus 1 power times 1 times 2 times 3 times up to p minus 1. So that's equal to p minus 1 factorial is gonna be congruent to 1 times 2 times 3 up to p minus 1. So that's p minus 1 factorial, everything mod p. And since p minus 1 factorial is not divisible by p, then I can just divide both sides by it. So I get a to the p minus 1 is congruent to a mod p. So QED. This is a basic proof of Fermat's Little Theorem. Now let's go back to our problem and see how we could apply this to solving our problem. So let's go back to our quest of making a to the b to the c look like a to the b. What we got from Fermat's little theorem is that anything raised to the p minus 1 will be just congruent to 1 mod p. Let's go ahead and see what b raised to the c would look like. So b raised to the c by the Euclidean theorem will be equal to some quotient times p minus 1 plus some remainder. Therefore, we can rewrite a raised to the b raised to the c as a raised to the q times p minus 1 plus r. And applying the rules of exponentiation that we saw in the previous video, namely that a raised to the b plus c is equal to a to the b times a to the c, we will get that this is equal to a raised to the q times p minus 1 times a raised to the r. And the other rule that we know is that a raised to the b times c is equal to a raised to the b everything raised to the c. So I can rewrite this as a raised to the p minus 1 everything raised to the q times a raised to the r. And as we saw, thanks to Fermat's little theorem, we know that this is equal to 1 and 1 raised to the qth power is always 1. So what we will get at the end is that this will be equal to a raised to the r. And r is precisely the modulo of b raised to the c with respect to p minus 1. So to summarize, we will be given a raised to the b raised to the c, and we saw that we can simplify this by replacing b raised to the c with the remainder of b raised to the c modulo p minus 1. So let's call r is equal to b raised to the c mod p minus 1. So this will be just equal to a raised to the r mod p. And we can do this in all of log c because we will require log c instruction for computing r times log r, because then we will require log r instructions to compute a to the r. So let's go ahead and check out our code. So this is our program. We will start by reading the number of cases, then we will process them. For each case we will need to input 3 values a, b, and c. Then we will compute r, our new exponent, and it's gonna be equal to the modular binary exponentiation of b raised to the c, and our modulo here will be mod minus 1. I defined the mod here to be 1,000,007. So I modified the modular binary exponentiation function from the previous problem so that it will take 3 variables. The first one is the base, the second one is the exponent, and the third one is the modulo I wanna use. And then after computing our exponent that we called r in our demonstration, I will output the answer, which is gonna be a raised to that exponent, and this time the modulo I'm using is the actual modulo. And let's go ahead and check out the implementation of our modulo binary exponentiation function. So as I said, I added a third argument here, that is the modulo, and it is pretty much identical to the implementation from the previous problem. So the base case, if the exponent is equal to 0, I'll just return 1. Then I will compute the result, which is the modulo binary exponentiation of the base raised to the exponent divided by 2. And then I will process the 2 cases, that is if the exponent is odd, then my answer will be the result, which is equal to base raised to exponent over 2 times base raised to exponent over 2. So I get the base raised to exponent times the base one more time because my exponent is odd, which is actually equal to exponent over 2 times 2 plus 1. And as I said in the previous problem, I have to break down these products into 2 products so that I won't have any overflow issues. And the other case is that the exponent is even, and in that case I'll just have to perform this multiplication here. So that's pretty much it. Let's go ahead and submit. So that worked. Thank you for watching. See you in the next video. Bye bye.